Okay, good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Dr. Arpan Chattopadhyay, and he'll be speaking on inverse extended Kalman filter. Dr. Arpan received the BE degree in Electronics and Telecommunication from Jadavpur University, Kolkata in 2008, and ME and PhD degrees in Telecommunication from IISc Bangalore in 2010 and 2015, respectively. He's currently working as an assistant professor with the Electrical Engineering Department, IIT Delhi. Previously, he held postdoctoral positions with the Electrical Engineering Department, University of Southern California at Los Angeles, USA, and INRIA ENS Paris. His research interests include wireless communication and networks, cyber-physical systems, network estimation and control, and reinforcement learning. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Arpan directly. Over to you, Dr. Arpan.
So thanks for the introduction, and thanks a lot to CNI for inviting me for this talk. So today I will give you a brief overview of our recent works on inverse extended Kalman filter. So this is a joint work with Himali Singh, who is my PhD student at IIT Delhi, and Dr. Kumar Vijay Mishra from US Army Research Lab. He is collaborating with us. So Himali is present in this audience today. So, so this talk will be quite, the work is quite lengthy. So I don't think I'll be able to cover all the topics in details, but I will try to give an overview of each of these topics and go deeper in for some of these topics or some of these areas that we have worked on. So the basic idea here is to give the audience an overview of this particular line of research, which has become very popular these days. So let's start with the motivation. So the motivation of this particular work comes from the need to design and analyze counter-adversarial autonomous systems. So these systems are typically complex systems and they are dynamical in nature. They involve cognitive sensing of the environment, and there are multiple agents involved in such systems. So typically people model the systems with two agents, but there could be multiple agents. So these agents are intelligent and cognitive, and you can imagine that there could be an attacker and a defender in a two-agent system where they are working against each other. And so basically we want to capture the interaction between these two competing agents, but not in a game theoretic sense in this talk. So here are some examples which or some applications which can be categorized as counter-adversarial autonomous systems applications or problems. So one of them is inverse cognition, where so basically you have two agents, one defender and one attacker. We are calling them attacker and defender for the time being. So the defender, what the attacker is doing is that it's trying to gather some information about the defender. And the defender, on the other hand, it's trying to learn the information that the attacker is gaining about the defender. So that's why it's an inverse cognition problem. So for example, imagine that there is a cognitive radar which is trying to infer or estimate the location of a target. And the target, on the other hand, wants to estimate the estimate made by the radar. So basically its own position, the target is trying to estimate its own position as inferred by a cognitive radar. Then there are inverse reinforcement learning problems. So in typical reinforcement learning problem, there is a state action sequence. So the reinforcement learning agent observes a particular state and accordingly chooses an action. And based on the current state and current action, it gets a reward and it wants to maximize its reward over a time horizon. Now in inverse RL, there is an inverse agent which observes the sequence of state action pairs of the reinforcement learning agent. And from that, it tries to infer the reward function of the reinforcement learning agent. So let's zoom into the some specific inverse cognition examples. So the first one is inverse filtering, which we will discuss today, but let me give you a brief overview about it. So imagine that there are two agents. In this particular picture, you can see there is a radar and there is a target. So the radar will also be called an adversary in this talk, and the target will be called as a defender, or it could be us also. Like we are interacting with an adversary. So I will use all these terms interchangeably throughout the talk. So the target has a state xk. It could be the position and velocity of that particular target at time k. Time k is a discrete time index. So the radar sends electromagnetic pulse, and from the reflected signal, it tries to infer xk. So basically, radar will compute x hat k, which is the estimate of the target's state. Target has a state xk, and it's exerting a control uk at time k. Now, on the other hand, when the radar estimates this x hat k or computes x hat k, it chooses an action ak. Now, what is ak? What is the action of the radar? It could be the signal waveform that the radar is choosing, or it could be the angular beamforming pattern that it's adopting. So that's the action of the radar. And the target, on the other hand, it can see the action of the radar because it can see what signal it's receiving. Now, based on this receipts, based on the observed action of the radar, the target wants to infer what is x hat k, what is the radar estimating. So basically, the target is computing x double hat k. And the topic of today's talk is how can the target compute this x double hat k, and what are its properties. So there are other examples of inverse cognition. Say, for example, interactive learning model, where there is an instructor who is teaching a particular learner, and he wants to infer how much the learner has absorbed. So that this is again an inverse problem, inverse learning problem. Then there could be cybersecurity applications where there is an attacker and there is a defender. The attacker wants to figure out, the defender wants to figure out what the attacker is thinking about itself. And on the other hand, the attacker is also trying to infer what is the defender's strategy and what is the defender's belief on the possibility of an ongoing attack. So these are all inverse cognition problems. Now, today's talk is about inverse stochastic filtering. So all of us know that inverse filtering is a classical topic where basically there is a transfer function hf, and you want to design a filter with transfer function 1 by hf. But inverse stochastic filtering is a very new topic. So this field was particularly started by this paper of Vikram Krishnamurthy and Muralidhar Rangaswamy in 2019. They have conference versions of this paper, but I am just citing the journal paper. So in this particular paper, they talked about how to design an inverse Kalman filter. So basically, the name of the paper is how to calibrate your adversary's capabilities. So that's the topic of this paper, an inverse filtering for counter-autonomous systems. So then Vikram Krishnamurthy and his colleagues and collaborators and his group members and collaborators, they have done a lot of work on this topic. Some of them I am just mentioning. So one is inverse filtering for hidden Markov models with application to counter-adversarial autonomous systems. And this particular paper is very interesting: adversarial radar inference, inverse tracking, identifying cognition, and designing smart interference. It appeared in 2020. So the specialty of this paper is that here the inverse agent is trying to infer the utility function of the radar. And for that, it's using some theory from microeconomics, which is called revealed preference theory. Specifically, they use a particular theorem called Afriyat's theorem from microeconomics. So that's the beauty of this paper. So there are a few other tangential works on inverse problems. For example, this particular work in ICAS 2022, which talk about how can a cognitive radar mask its cognition. Then there are works on inverse sequential hypothesis testing, and also inverse reinforcement learning. This is a very recent archive report that I have noticed. So these are tangential. So I will not go into the details of this. So I will talk, now let's come to our contributions, what we have done in our work. So we have designed inverse filtering algorithms for various versions of extended Kalman filter, namely inverse EKF with unknown input, inverse EKF without unknown input, which is standard EKF basically, inverse inverse of the standard EKF. Then inverse Kalman filter with unknown input. It turned out to be a byproduct of inverse EKF in our problem. Then some variations of EKF such as Gaussian-sum EKF, second order EKF, and RKHS based EKF. RKHS stands for reproducing kernel Hilbert space. So I will talk about these things from a very high level, but I will try to give you a brief overview of what each of these inverse filters are. Then we'll go to stability analysis. So we have results for inverse EKF without any unknown input. We have stability analysis for that, which is brand new. Then inverse second order EKF, and also inverse Kalman filter with unknown input. So we'll provide sufficient statistics for the sufficient conditions for the stability of these inverse filters. So let's start with the various inverse EKFs. So let me explain the system model, which is very standard, but still it's better to explain it. So there are two agents. One is us, like we are one agent, or we are the defender, or you can imagine that we are the target, and we are interacting with an adversary, which can also be called as an attacker, or the adversary could be a radar in a radar target context. So our state evolution, or the target state evolution, is this: xk plus 1 equal to f of xk comma uk plus wk. This dynamics is known to us, but it's not known to the adversary. So f is a nonlinear function, xk is the state at time k, and uk is the control action that we are exerting at time k. Wk is the state noise, which is modeled as a Gaussian random variable, a Gaussian random vector. Then the adversary is observing yk, which is h of xk comma uk plus vk. Vk is again a Gaussian observation noise. Now from this observation, adversary finds x hat k, which is the estimate of xk. Then the adversary chooses an action, which is ak, which is g of x hat k. But when we observe it, we observe a noisy version of this action. So we observe g of x hat k plus epsilon k as the action of the adversary. And epsilon is again chosen from a Gaussian distribution. Now, based on our observation, so our observation is basically AK, this action of the radar. So based on that observation, we estimate x double hat k. So basically, compute x double hat k, which is an estimate for x hat k. Now, if the system, so this is the system model for a nonlinear system. If the system is linear, then all these equations become linear equations. Xk plus 1 equal to fxk plus buk plus wk, and similarly for observations and this action ak. So in this talk, we make some assumptions. The assumptions are that all noise terms are mutually independent and IID across time. All functions and noise covariance matrices are known to both agents, but we will see later how to relax this assumption. Number 3, each agent knows its own state and action, but the other agent may not know about it.
Arpan, a quick question.
Yes.
Okay, if you can go back to the slide. Yeah. So I can understand that the adversary doesn't know the xk and therefore is trying to estimate it, and x hat k is the estimate, and there is some loss function for the for a bad estimation. But then you also say that we are estimating x double hat k. Can you explain in the context of this model? Is it an estimate of x hat k, or is it an estimate of ak?
It's basically it's a small mistake. So we are estimating x hat k. So x double hat k is the estimate of x hat k.
So your loss function is between x double hat k and x hat k.
Right.
Okay, thank you.
So the application could be something like this. So suppose you have a radar and a target, and the target, if the target knows what is the estimate made by the radar, then it knows into which direction it should fly. Say, for example, to evade a missile fire by the radar.
Isn't it better to look for an estimate of the AK rather than the x hat k, because the AK includes the noise?
No,
so
AK typically would be, I mean, that could be one possibility, but AK is typically the radar's waveform or beamforming pattern that the radar is choosing. So that's different from whether the radar in a warfare situation. So suppose the radar is shooting a missile, so the target wants to avoid that or evade that particular missile fire. So for that, it has to know what the radar, what estimate the radar is making about its own about the target's location.
The point I would contend, which is important, is the actual action that the radar takes to send to launch maybe whatever it is doing. And so it appears that AK with the epsilon k is perhaps the more important thing to estimate than x hat k. Anyway, I think
okay,
perhaps it's a point of view. Yeah, please go ahead.
So let's treat it as a mathematical problem for the time being and proceed. And later, I think we can discuss on this.
Sure. Please go ahead.
Okay. So the first case. So you have this radar and target setting. Now we are talking about forward EKF without direct feed through. What does it mean? It means that in this special case, this YK does not depend on UK. So it's only a function of HK. So our control does not affect adversary's observation. So standard EKF does the following. It linearizes the nonlinear functions via first order Taylor series expansion and then use Kalman filter equations. And if you're familiar with this, then the EKF equations will look something like this, which is similar to a Kalman filter, but there are some modifications because you have a nonlinear function. If the dynamics is nonlinear and the observation functions are also nonlinear. So now, what is the idea to design this inverse extended Kalman filter? Now, in this particular case, it turns out that for the I-EKF, observation is AK, and it's trying to estimate a particular state. What is that state? The state turns out to be an augmented state ZK, which is x hat k and u hat k minus 2. What is why x hat k? Because I want to the target wants to estimate the radar's estimate. That's why the state x hat k is in the target in this augmented state. Also, the target is actually exerting some control input, which is not appearing in YK, but it's controlling the dynamics of the target. So this u hat k is also being UK is also being estimated by the radar, and target wants to know what is the radar is estimating about u hat k, about UK. So that's why this u hat k minus 2 also appears in this augmented state. There is a reason why we are not having u hat k and instead we are having u hat k minus 2. There is a time delay involved in this process. That's why we are having u hat k minus 2 and not u hat k directly. So I'm not going into the details of that. So now for the target, ZK is the state, and we know the dynamics. We know how ZK evolves over time, and AK is the observation. So now again, the target can use the principle of extended Kalman filter, and it can try to estimate ZK. So that's the key idea. So it turns out that the estimate x hat k made by the radar evolves something in this way. So it's a function f tilde k, for which we have a closed form expression, but we are not writing because it's too long. So x hat k plus 1 is a function of x hat k, u hat k minus 2. These two combines to zk. Then x hat k minus 1. Then this xk and xk plus 1, vk and vk plus 1. And similarly, u hat k minus 1 also has this dynamics. And these two equations govern the state evolution which is basically being tracked by the inverse filter at the target. Now, let's see. So basically, this augmented state dynamics can be handled by EKF at the inverse agent. In this particular equation, you can see that this x hat k minus 1, this is basically not known to the inverse agent, because this x hat k minus 1 is being, it's the estimate made by the radar, and the target does not know it. But the target has already estimated x hat k minus 1. So we are making an approximation that this x hat k minus 1 is approximated by x double hat k minus 1, which the target has already estimated. And this xk and xk plus 1, these appear in this dynamics. These quantities are not known by the radar, but they are known to the target. Why? Because they are the state of the target. So the target knows its own state. So the target knows xk and xk plus 1. And this vk and vk plus 1, they appear to be noise. So these are nonlinear evolutions. And we can use, for the inverse filtering, we can use the standard results of inverse of forward EKF without direct fit through. And we get this particular equation for inverse filtering, set of equations. So basically, we have a prediction step where we are calculating x double hat k plus 1 given k recursively. Then we have so we have a smoothing step here, u double hat k minus 1 given k. So this requires some particular treatment, like replacing this x hat k minus 1 by x double hat k minus 1. And we have updates for the gain matrices as well as for the covariance matrices. Now, with direct fit through, again, we can use very similar principles. So, but in this case, what happens is that the yk is dependent on uk also. Earlier, without direct fit through, yk was independent of uk, but now the radar's observation yk is dependent on the target's action uk. So that's the difference. So again, here this is the forward extended Kalman filter with direct fit through. We already have this equations available which govern how the forward filter will estimate the target state. So these are standard results. For the inverse filter, the idea is to consider the augmented state zk. In this case, it turns out to be x hat k and u hat k. There is no u hat k minus 2. It's u hat k because there is no delay involved in this. And because this fit through, direct fit through actually helps in estimating this u hat k. That's why we are having x hat k and u hat k. So this is the state that is being tracked by the inverse filter at the target. And the observation is AK. And then you use standard extended Kalman filter techniques on this state and observation sequence. We can write x hat k plus k and u hat k recursively in this form. We have closed form expressions for them. So we can do this. And similarly, inverse of extended Kalman filter without any unknown input and inverse Kalman filter with unknown input, both of them turn out to be special case of these two cases of these two problems, inverse filter EKF with unknown input. So they turn out to be special cases and they can be handled in a similar fashion. So there is no new special theory in these two cases. Okay, any questions so far? Okay. So then we also have derived inverse filters for second order EKF. So the key second order EKF basically does the following. So in standard EKF, we know that we are doing first order Taylor series approximation of the nonlinear functions, but here we are using second order Taylor series approximation. So that's the main difference. And accordingly, we will get new set of updates for the second order EKF. This is the forward second order EKF, where you can see that the apart from the Jacobians of this function f, we are also getting Hessians in the update because we have a second order EKF. Now, similarly, by using similar principles as before, we can use we can derive update equations for inverse second order EKF. So you can see we are computing x double hat k plus 1 given k in terms of x double hat k. So x double hat k is basically one-step prediction, and x double hat k plus 1 given k is basically two-step prediction value. So, and we have update equations for both x double hat k plus 1 given k and x double hat k. So we have both versions of second order EKF, inverse second order EKF. So I am not going into the details of this, but just let me assure you that we have derived these things. Then we have also considered Gaussian-sum EKF, where the idea is that in the forward filter, in a Gaussian-sum EKF, you assume that the posterior distribution of xk given y1, y2 up to yk is approximated by a suitable Gaussian mixture distribution, where the CIKs are the Gaussian mixture coefficients, and this x bar ik and sigma ik's are the mean and variance of this Gaussian distributions. And then you update this CIKs, you can have Bayesian update of this CIKs, and also you can have recursive updates of this x bar and sigma values. So what we have done is we have basically we could derive the inverse filter for this Gaussian-sum EKF, and we could actually show that if we maintain this augmented state zk equal to x bar ik comma cik for all I between 1 to L, then this produces the inverse filter for this Gaussian-sum EKF, which again turns out to be a Gaussian-sum EKF. So the inverse filter is also another Gaussian-sum EKF. So using very similar techniques as before, there is nothing new. So with this, I will conclude this particular subsection of deriving inverse filters for various versions of EKF. So I hope by now the audience has a clear idea of what inverse filtering is and how to derive them. So now comes the main results, the stability results, which are the most challenging part of this work. So we have results for 2-3 cases. The first one is inverse Kalman filter with unknown input without direct feed through. So let us recall the model again. So we have xk plus 1, which has this linear dynamics, yk, which is hxk plus vk. So we don't have direct feed through. So the uk, the control input of the target, does not affect the observation of the radar. AK, the action made by the radar, is g into x hat k plus epsilon k, or this is the action of the radar as observed by the target. So these are the forward filter equations. These are standard. We have not derived them. These are available in the literature. What we have done is we have derived the inverse filter updates for this particular forward filter. And in this case, again, actually, we have seen that this xk plus 1 in this prediction state, we have xk plus 1. So remember, this inverse filter is being run at the target. Xk plus 1 is known to the target. So this can be treated as an exogenous, non-exogenous input. So this is a known quantity. Nothing fancy about it. So very similar to the inverse extended Kalman filter without direct feed through. Now here is the main result in this case. So we have some matrices. If you come back to this, we have this M matrix and this K matrix in the forward filter. And similarly, in the inverse filter also, we have some certain matrices, gain matrices and covariance matrices. So this theorem says that consider an asymptotically stable forward Kalman filter without direct fit through, such that the gain matrices MK and KK asymptotically converge to limiting gain matrices M bar and K bar. Okay, respectively. The measurement noise covariance matrix epsilon sigma epsilon is positive definite, which is obvious. Denote the limiting matrices F bar with, by this expression and Q bar with this expression, where E bar and E bar has a closed form expression. So then the inverse Kalman filter without direct fit through is asymptotically stable under the assumption that the pair F bar G is observable. So F bar is a matrix associated with the inverse Kalman filter. This should be observable. This F bar comma G should be observable, and the pair F bar comma C should be controllable, where C is the square root of this Q bar matrix. So I'm not giving you the not the physical meaning of this A bar and K bar matrices, because that will take too much time. I just wanted to give you a flavor of what the theorem looks like and what kind of results we have. So basically, it says that we have asymptotic stability for the inverse filter under certain conditions, provided that these matrices converge to some desired limiting values. Remember, this theorem only provides sufficient condition for stability, but not necessary conditions. And the proof actually involves writing the inverse Kalman filter estimate, error dynamics, and the covariance dynamics in a recursive form, use Riccati equation for the inverse filter, and use the usual spectral radius bound for stability. Say, for example, if you know, if in a linear system, if you want to show that the linear system is stable, then a sufficient condition for that is that you show the maximum eigenvalue of a suitable matrix is less than 1. So we apply the same principle here and obtain this particular theorem. And we exploit the Riccati equation for the inverse filter. Yes, Rahul?
So stability over here, is it stochastic stability or is it in the mean sense?
So basically, the max eigenvalue is less than 1. So you can say that in a mean squared sense, it's stable.
Okay.
Okay, so let's now go back to extended Kalman filter and inverse extended Kalman filter. So to derive or to establish the stability of inverse extended Kalman filter, we have adopted two approaches. Each of them have their own has its own advantage and disadvantage, and we will explain them. The first approach is bounded nonlinearity approach, which is very similar to standard Lyapunov-Drift-based techniques. I will explain that. So the problem is it is hard to establish it in our problem. We have done it, but we have been able to establish it partly, not fully. And we have seen that this paper in TAC 2019 by Rao et al. So they actually did a very popular work on EKF stability, where they used this particular approach, but they also could not establish this Lyapunov-Drift criteria completely. Basically, they could not verify this criteria completely. So that's the problem with this approach. But Lyapunov-Drift is a standard technique, so I just decided to include it in this talk. Then the second approach is unknown matrix approach. So this is slightly different. So basically, if you write the Taylor series approximation of the dynamics, there are some certain higher order terms which appear as an offset term in the dynamics, and you cannot capture it directly through the linearization. So what you do is, for the offset term, you remove the offset term, you ignore the offset term, and instead you introduce some multiplicative matrix, instrument matrix in a multiplicative form, and that captures for the offset that was created by the nonlinearity. So I will also come into the details. I will explain how this works. And it comes from this particular paper appeared in Automatica 2012. So let's come to the first approach, or a bounded nonlinearity approach. So let's go through some definitions which is borrowed from this particular paper in 1999. A stochastic process zeta k is defined to be exponentially bounded in mean squared sense if there are real numbers eta, nu, and numbers lambda less than 1, such that this happens. Expectation of norm of xi k square or zeta k square less than equal to eta into lambda power k into expectation of zeta naught square plus nu. This should hold for every k. And the boundedness is said to hold with probability 1 if supremum over all k, norm of zeta k less than infinity, with probability 1. So we have two types of boundedness. One is mean squared sense, the other one is in probability 1. And we are still calling it exponentially bounded as shown in this definition. Then this paper by Rife et al. So they actually provide a sufficient condition for exponential boundedness of a particular stochastic process. So it's very similar to the Lyapunov drift condition. What it says that consider a function vk of xi k and real numbers v mean vmax, mu, and lambda. Lambda is less than equal to 1, such that for all k, this vk of xi k is upper bounded and lower bounded by these two quadratic functions, v mean into norm of xi k square, zeta k square, and vmax into norm of zeta k square. So it's basically vk of xi k is order of zeta k square. And the mean drift of this vk function, so expectation of vk plus 1 of zeta k plus 1 given zeta k minus vk of zeta k is less than equal to this, mu minus lambda vk of zeta k. If these conditions are satisfied, then the stochastic process zeta k is exponentially bounded both in the mean squared sense and also with probability 1. So the first is the definition of exponential boundedness. Then this particular drift condition is gives a sufficient condition for exponential boundedness. Now, in the forward or inverse EKF, you can view the error process as zeta k and use this condition to provide sufficient condition for, use this theorem for sufficient condition of exponential boundedness of the error process. That's the idea. So, so let me first explain the result from this Rife et al. Paper. So, you know, we have this nonlinear dynamics if, and if you expand it as a Taylor series, then f of xk minus f of x hat k turns out to be this, where fk is the Jacobian, and this phi is a higher order term. Basically, we are taking first order Taylor series approximation, so we are getting a higher order term phi. Right? And similarly, if you have if you write this h function in first order Taylor series expansion, then again you get a nonlinear term chi, which is a function of xk and x hat k. So the theorem of in this 1990 paper says the following. So this theorem is about the exponential boundedness of the error process of forward EKF. So what they say is that suppose there are some positive real constants such that these conditions are satisfied, meaning this sigma k matrix is bounded between sigma L into I and sigma U into I, where these inequalities are semi-definite inequalities. Basically, sigma k minus sigma L I should be positive semi-definite. So that kind of inequalities. Then Qk is also bounded, Rk is also bounded, and you have some bound on the Jacobians of the F and H matrices as shown in condition 1. Can you see the cursor, a mouse pointer?
Yes.
Yeah. So these are, suppose these conditions are satisfied. Also, let's assume that the Fk is non-singular for every k. And the third important condition is that this phi and psi, and phi and chi, these nonlinear terms, they are bounded by this quadratic functions. So norm of phi, to norm of this phi x comma x hat less than equal to some constant into norm of x minus x hat whole square for x norm of x minus x hat less than equal to some constant. And similarly for chi. So this third condition actually amounts to this bounded nonlinearity assumption, or the name that appears in this approach, bounded nonlinearity approach, that comes from this third condition. Now, this paper actually says that if these three conditions are satisfied, then the error process of the forward EKF is exponentially bounded in the mean squared sense and with probability 1. Now, here is the catch. So when we read this paper, we found that this is not completely true, because what they could actually establish is that if the estimation error is always bounded within a suitable epsilon ball, then they can prove exponential boundedness. So the assumption that they missed, or maybe they overlooked, is that the error process is always within some epsilon ball. And under that assumption, if these three conditions are satisfied, then the exponential boundedness is actually guaranteed for the forward EKF. So, so we proceeded with this. We did not assume that the forward EKF is always stable. We under this particular condition, we assume that the forward EKF is stable. Now, with this, let's proceed to the stability results for the inverse EKF. So in inverse EKF, again, we have to linearize this G function, which is used by the radar to choose its action. And there we have this nonlinear term chi. So our theorem says that suppose the forward EKF assumptions or conditions are satisfied already, and additionally these few conditions need to be satisfied, like this RK bar, sigma k bar, and GK, which are associated with the inverse filter. They should be bounded according to some suitable according to these bounds. HK should be full column rank for every k. Remember, HK is a Hessian matrix, which is a random matrix. So it should be a full column rank for every k. And number 3, this nonlinear term chi bar, it should be bounded by this kappa, by this constant into this non-square function. So basically, similar to the forward EKF, we also need to bound this nonlinear term using this quadratic upper bound. So then we could show that the error process of the inverse EKF is exponentially bounded in the mean squared sense and with probability 1. Again, provided that the estimation error is always bounded within a suitable epsilon ball. Then we can actually say that it's exponentially bounded. Now, this is not a complete stability proof, because we are cheating. We are already assuming that the estimation error is within a suitable epsilon ball. So this approach, while it's very appealing because of the Lyapunov drift thing, but in our proof problem, we could not establish it completely. But using this approach, actually, we also partially prove the stability of second order EKF and inverse second order EKF. So there was no result available for the stability of second order EKF, even for the forward filter. So we derived stability conditions for both, but with this small amount of cheating. Assumptions were very similar, but we needed constraints on Hessians because we are using second order EKF. So we had some Hessian matrices which needed to be bounded. And this bounded nonlinearity term, which were bounded by a quadratic function earlier, now because we are going to second order EKF, so we had to bound it by a cubic term. And this stability proofs in general involve many metric theoretic techniques. The proofs are quite long, but they are very, and they are very involved actually. But I cannot give you the detail because then time will run out. Then we will come to the second approach, which is unknown matrix method. Now in the unknown matrix method, so it's a standard EKF without any unknown input we are considering. So in the unknown matrix method, we want to get rid of this condition that the error should lie within an epsilon ball. We want to get rid of that assumption. So for that, we are using an unknown instrument matrix to compensate for the bounded nonlinearity term. So let's write the error process in this way. So, let's still consider the forward EKF, and and we are trying to establish its stability by using this unknown matrix approach. So x tilde is the error process for the forward EKF, which is xk plus 1 minus x hat k plus 1 given k. So x tilde is the error process for the forward EKF, remember. Similarly, x tilde k is xk minus x hat k. And similarly, we can define these things y tilde k, which is yk minus y hat k, where y hat k is this h of x hat k plus 1 given k. You don't have to understand this for the time being because it will take too much time. So in the previous case, in the bounded nonlinearity case, we had this x tilde k plus 1 given k, which is the error. It's written in this form: a linear term xk minus x hat k. This is the estimation error, plus some wk, which is some noise term, plus some function, plus some offset, which is a quadratic term. Now, in this approach, what we are doing is we are saying that we will ignore this offset term, and instead of that, we will introduce an instrument matrix UKX in this dynamics, such that this UKX suitably captures the effect of this offset term. UKX is not a constant matrix; it could be variable. It could depend on this estimate that that is there in the second order term. So it's a sample path dependent matrix, and it's variable, and it's unknown to us. But let's assume that the dynamics of this error process can be written in this form. And similarly, for this yk also, or y tilde k also, we do similar thing. We incorporate some, in order to compensate for the offset terms, we incorporate this multiplicative matrix uky, which is an instrument matrix, and we accordingly write the dynamics of this y tilde k. I hope the brief idea is clear, the high level idea. The offset is replaced by this, compensated by this multiplicative matrix. Now, using this multiplicative matrix terms, we can write the dynamics of x tilde k without any offset term. But this dynamics, when you write it, you find that UKX and UKY appear in this dynamics. And I have highlighted those matrices by the blue matrices. So what we have done is, we have, I will not state the theorem here, but we have provided sufficient conditions for exponential boundedness of the prediction error x tilde k plus 1 given k, and the estimation error x tilde k using this instrument matrices. So we have results for both EKF and inverse EKF as in the bounded nonlinearity approach. For this, to establish stability, we had to use a quadratic Lyapunov function, which we have designed. But this proof required certain conditions on various non-constraints on the Jacobian and other matrices, and also we needed some conditions on this new instrument matrices that we have introduced. The problem is these instrument matrices are sample path dependent, and in general, the gradient matrices involved in the dynamics, they are also sample path dependent. So the conditions that we need, they are not easy to verify. So that's a big problem with both these approaches. We don't have an easily verifiable condition for stability of this forward and inverse filters. But if those conditions are satisfied, they are sufficient for stability of the filters. Now, the advantage of this unknown matrix method is that we don't need this epsilon ball constant assumption. We can guarantee exponential boundedness of the error without assuming any constant on the error. So we get rid of the cheating. That's all. So how much time do I have now?
Another 5 minutes.
Okay. So now I will just briefly go over the techniques that we can use for unknown system models. So far we have assumed that the system model is known to both the agents, to the radar as well as to the target. Now, if the system model is not known, say for example, if some particular function is not known, then what we do is we actually use that concepts from reproducing kernel Hilbert space or RKHs. So for example, what could happen is that the adversary may not know the state transition of the defender. The defender may not know how the attacker, what is the control rule adopted by the attacker. So the solution is we assume that the unknown function lies in an RKHs or reproducing kernel Hilbert space. And in our work, we specifically considered Gaussian kernel. So I will not explain this, but those who know RKHs, they will understand. So for that, we considered a set of dictionary x bar m for this kernel. And we define a function psi x using this kernels. So basically this psi, when we design this psi x, we use the vectors from this dictionary and we define the suitable function psi x. So basically the idea here is that the unknown function will lie in a suitable function space, which could be spanned by a set of functions that we are generating through this kernels. And then let's assume that the defender doesn't know the estimation rule of the adversary and the control rule of the adversary. So what it does is it assumes that the adversary's model is this: x at k plus 1 equal to b into psi of x at k plus w bar k, where this w bar k is coming from some unknown Gaussian distribution. And similarly for the action taken by the radar is generated through this particular dynamics. So we have linearized the dynamics. It was a nonlinear dynamics. Now we have linearized this using RKHs. But we have this unknown things, unknown parameters. This B matrix is not known to us. We have to estimate this B. C is also unknown. Q bar is unknown. R bar is unknown. So we define this unknown parameter theta bar and learn this theta bar via online expectation maximization algorithm. And it turns out that with some minor approximations, we can have closed form updates for this theta bar, for these unknown parameters. So the updates are recursive. They so basically at every time k, so at every time step, we are actually updating theta bar only once. So we are not running the entire EM algorithm for at each iteration. At each iteration, we are running one iteration of theta. So that's the beauty of this algorithm. And then using this and using some suitable augmented state, we can write the equations for inverse RKHs EKF. So it's an inverse extended Kalman filter, which is using concept from RKHs. And the dictionary is also updated recursively. We have techniques for that. So I will not go into the details of numerical works, but I will just highlight one interesting thing that we have compared the performance of the forward EKFs and inverse EKFs for various cases with something called the recursive Cramér-Rao lower bound. And we have shown the performance with respect to the recursive Cramér-Rao lower bound for various cases, basically Kalman filter and inverse Kalman filter, EKF, second order EKF, Gaussian-sum EKF, all these filters. So in the case of Gaussian-sum EKF, it turned out that if you have more number of Gaussians in the mixture distribution, then the filters perform better, which is quite intuitive, because then it actually the mixture distribution can approximate the unknown distribution more precisely. We also have results for RKHs EKF. Because due to lack of time, I will not go into the details, but we have actually considered various cases where basically the forward filter knows the dynamics of the the target, or the forward filter does not know the dynamics of the target, whether the inverse filter knows what is the structure of the forward filter. We also have considered the cases where the inverse agent does not know the structure of the forward filter, so it assumes that so forward filter is using some a specific filtering rule, but the inverse filter is assuming that the forward filter is using some other filtering technique. So what is the effect of this mismatch? All these things we have considered in our simulations. So I will not be able to explain them, but I will just highlight the key takeaways from the numerical works that we have done. The first important observation from numerical works that we have done is that there is no specific ordering between the error performance of the forward filter and inverse filter. It can be smaller for inverse filter, or it can be larger for inverse filter. The reason is obvious. They are trying to solve two different problems. They are not trying to solve the same estimation problem. Number two, knowledge of the other agents. Sorry, I think it's a mistake. Knowledge of the other agent strategy actually facilitates estimation. So if you know about the other agent, then you can estimate more accurately. So that's the second observation. Then in the third observation, we have found that even though the EKF, the extended Kalman filter, assumes complete knowledge of the model, still the RKHS can sometimes outperform EKF, even though RKHS does not assume any specific model for the process. Why does it happen? Because EKF, even though it assumes a complete model knowledge, it performs a first order Taylor series approximation of the unknown functions. Whereas on the other side, this RKHS EKF does Gaussian kernel approximation, which can be better than this first order Taylor series approximation in some specific applications. So it is perfectly possible that RKHS EKF outperforms EKF. Okay, so this almost concludes today's talk. I will just summarize. So far what we have done is we have derived I inverse EKF and its variants with and without unknown input. We have done stability analysis for some of them using two approaches, a bounded nonlinearity approach and unknown matrix approach. And we have also handled the unknown model case by using techniques from reproducing kernel Hilbert space. Now, having said that, there are still some open issues that need to be addressed, and which either we did not address because of lack of time, or we could not address because they are too hard. So the first one is that our stability conditions are not easily verifiable. They are sample path dependent. So we don't know how to alleviate this problem. For the time being, for now, it's just an open problem. Then there is a possibility of deriving inverse filters for other nonlinear stochastic filters, which we have not done yet. We are doing a number of them, but it's not complete yet. Number three, stability results of RKHS EKF and its inverse is still open. We are working on that. Hopefully, we'll be able to do it in near future. Number four, extension of these results to time varying systems is still open. Like, is there any stability result guarantee that you can provide for time varying systems? That's still open. Number five, we assume that the forward agent is not strategic. So imagine that both the agents are strategic and they are interacting in this setting, in this inverse filtering setting. Then how to model that setup, that problem, is still an open question, and I think it will be very interesting. And I hope that this problem area interests many of you, and maybe some of you can take up this problem in the future. So with this, I will conclude, and I will be happy to take any questions right now or over email. If you have any question later, then you can contact me over email. Thanks.
Thank you, Dr. Arpan, for an informative talk. We can take one or two quick questions now. Are there any questions?
Is there any question in chat box? Yes. Oh, no, this is a comment. Okay. So,
Okay, if there are no questions, then maybe we can wind up the session for today. Thank you, Dr. Arpan, again for agreeing to talk at the CNI Network Seminar Series. And as discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. And the link to the recorded video will also be posted on the webpage. Thank you and have a great evening.